Boy, did it straighten back out quickly. Pretty stable, huh?
Again, high dihedral effect. This was a problem that made the ship difficult to fly throughout the entire program. And there's only one place that the entire propulsion system is complete. It has just one valve which goes open or closed, and it operates at room temperature. And I'll tell you, you don't even need to go to Stanford to be able to design a good valve to do that.
3 people working on a rocket meant for a Virgin Galactic spacecraft died in 2007 after it exploded at the Mojave spaceport.
Before we actually send anybody up, especially my children, since they're going in their first flight, you know, we will have tested this space rocket many times, and we want to be absolutely sure that anybody flying on Virgin Galactic gets a return ticket.
That's what we're here for today, is to investigate the loss of the reusable launch vehicle and the fatality and injury that occurred as a result of that.
According to an FAA spokesman, the Unity space vessel did not follow the flight plan previously agreed on. The agency barring Branson Space Tourism Company from flying its Spaceship Unity 2 rocket during the investigation.
Every time you get in a vehicle, you are, in effect, rolling a dice. Roll a 1 and you won't come home at the end of the day. For your car, that dice has about 5 million sides. For a commercial airliner, it has about 11 million. In the case of the space shuttle, the dice had only about 65 sides. Every time we make a safe journey in a vehicle, however, more sides are added to the dice. We can never be 100% certain how many it has, but the more safe trips we take, the more confident we can be that the dice has an increasingly higher number of sides. Of course, fatal incidents dramatically slash the number if and when they occur. Virgin Galactic operate a commercial launch system. For $400,000, you can roll their dice. However, in this video, I'm going to argue that no one is able to estimate the number of sides on Virgin Galactic's dice. This is a topic I've wanted to talk about for years. It's also a tricky one. Space tourism is a popular topic for discussion at the moment. There's been growing talk in recent months about exactly how safe Virgin Galactic's experience is. Unfortunately, many of these discussions focus on aspects such as the company's funding, its enigmatic figurehead, and other somewhat irrelevant factors. I'd instead like to collate everything known so far about the company's safety philosophy, design choices, and working procedures. So, we're going to head into this presentation with the following conditions. I'm not an aeronautical engineer. Even if I was, I wouldn't be able to entirely critique the design of Virgin Galactic's launch system, as much of it is not disclosed to the public. So, please consider this a presentation on the dangers of not understanding and properly communicating risk. There are many comparisons between the recent OceanGate incident and Virgin Galactic. Some are superficial, some are difficult to brush off. We must note that Virgin Galactic have expended much more effort into safety. Due to the inherent dangers of spaceflight, that does not necessarily make their system safer than OceanGate's, however. They may indeed be doing nothing wrong at all. It's just that there may be no demonstrable way to do what they're doing. As Virgin Galactic are a publicly traded company, almost all of their technical assessments take place behind closed doors. Therefore, it's impossible to obtain detailed design documents. Everything discussed here is based on publicly available information. Where none is available, that will be noted and contribute to our final conclusions. As we'll see shortly, the majority of spaceflight is orbital. Virgin Galactic performs suborbital flights only. As such, we'll not be directly comparing their system to orbital spaceflight systems. Some will get a mention, but only to discuss relevant historical incidents. This presentation was originally to cover Virgin Galactic and Blue Origin. Blue Origin faced similar issues due to the lack of safety transparency. However, they've gone through a more comprehensive test program and have a number of more visible and conventional safety provisions. So, while I decided to make this presentation solely about Virgin Galactic, do not take it as an endorsement for Blue Origin. I would still not fly on their system, even if offered it for free. Most of the organisations discussed here have, let's say, problematic figureheads. This video is not a billionaire showdown. We will focus on system design, legislation, and communication only. I can explain the differences between suborbital and orbital spaceflight in the time it takes Virgin Galactic to get you to space and back. So let's fire up a real-time animation and go for it. To begin, let's make sure we understand the vast gulf between suborbital and orbital spaceflight. The two are often lumped together in pop science writing, but as the saying goes, getting to space is easy, staying there is hard. Suborbital flight involves taking a ride on a rocket, usually pretty much straight upwards for a few minutes. With a sufficient amount of energy and a low enough mass, a relatively small rocket can get a crew high enough to be considered in space. Please note, we're not going to get bogged down in the definition of exactly where space starts. It's arbitrary. And that includes the Kármán line, by the way, which is neither fixed nor unambiguously defined. For the purpose of this video, let's just call it about 80 kilometers upwards and leave it there. Anyway, once you're up there, you get a few minutes of weightlessness as you round the top of a ballistic arc and then fall back down to Earth. It's not an easy task by any means to get there, but a world away from orbital flight. If you want to stay in space, you're going to need to go higher and a lot faster. SpaceShipTwo manages about 90 kilometers of altitude on a good day before falling back to Earth. At the point of apogee, and assuming a dry mass of about 5 tons, that's roughly 4.5 gigajoules of gravitational potential energy. So 4.5 gigajoules must be provided to the craft from its fuel, and the fuel on the carrier craft in the case of SpaceShipTwo. To get the same 5 tons orbiting at the height of the International Space Station, we'd need about 20 gigajoules of gravitational potential, and wait for it, 145 gigajoules of kinetic energy. That's 37 times the energy when compared to a suborbital flight for the same mass. And that's a huge simplification too. Once we factor in the need to accelerate the fuel itself and the associated structures as we go along, the energy requirements grow even more. And then consider the other end of the trip. All that energy is about the same that is output by a typical gas-fired power station working at full capacity for a couple of minutes. When we re-enter the atmosphere, that energy needs to go somewhere, and that somewhere is into heat. Again, we're not going to get bogged down in terminology. Ram heating, adiabatic compression, friction, whatever you want to call it, a re-entering orbital spacecraft and its surroundings are subject to comparable heating to the output of an entire power station for a few minutes. That requires a heat shield and advanced fluid mechanical considerations to ensure the craft doesn't burn up on re-entry. SpaceShipTwo's maximum speed is about 4,000 kilometers per hour. It's fast enough for skin heating to be a concern, and it requires material and design considerations, but nothing compared to an orbital spacecraft. So with us all on the same page, it's clear why getting 6 humans to orbit requires something that looks like this, but just getting them to space only requires this. From a research perspective, the gulf between suborbital and orbital spaceflight has very clearly been worth crossing. Only a tiny minority of crewed spaceflights have been suborbital. Though it is often said the mesosphere, that's the layer above the stratosphere, is the least well understood part of our atmosphere, as we have no way of staying there. However, there's never been much of a demand for crewed flights to this region for scientific study, as there's very little a crew can do in a 3-minute window. And this is why we must seriously begin to question the innovation value of any private suborbital operation. let's begin to get a sense of how safe Virgin Galactic's system could be. We're going to almost exclusively focus on the main vehicle, SpaceShipTwo, and not White Knight 2, which is the carrier vehicle. Both were largely designed by Burt Rutan, a figure we'll repeatedly refer back to. To begin, we're going to discuss where it sits in comparison to every other crewed suborbital vehicle. And to be honest, there aren't very many of them. I've broadly split them up into 3 categories, so let's work chronologically and see where each system fits. The first crewed suborbital launch system was Mercury Redstone. It was, in essence, a modified ballistic missile with a crew capsule strapped on top. And that puts it in our first category, vertically launched systems. Mercury Redstone had a total of just 2 crew flights to space before being retired. It went to space an additional 3 times uncrewed. Though somewhat anemic compared to its successors, I personally think it's the best looking rocket ever built. I even have a tattoo of it on my leg, actually. Anyway, 2 years later, the US Air Force asked the question, what is the smallest amount of plane that can be added onto a rocket engine and still have it fly? Subsequently, this gave birth to the X-15, the fastest aircraft ever flown. And this allows us to add in our second category, space planes. The X-15 went to space 13 times before being retired in 1968. A 36-year hiatus then followed for crewed suborbital flight. This was ended with the creation of SpaceShipOne. And this vehicle falls into my fuzzier third category of modern systems. I'm putting anything post-space race into this category. The reason is the advent of advanced computational fluid dynamics, finite element analysis, composite materials, and many other technologies make anything post-1990s almost impossible to directly compare with systems from the 1960s. SpaceShipOne was a spaceplane, so it fits into that category too. And to be absolutely clear, SpaceShipOne was the direct predecessor of Virgin Galactic's SpaceShipTwo and shares much of the design philosophy. It made 3 crewed flights to space. The next system to make it to space did so without a crew. Blue Origin's somewhat suggestive New Shepard system. It first made it to space in 2015 and carried out a total of 16 uncrewed flights between then and now. 2 of those didn't make it to space. Since 2021, New Shepard's taken crews to space successfully 6 times. It's a conventional vertically launched rocket with a crew capsule. And that brings us to SpaceShipTwo. SpaceShipTwo cannot be flown uncrewed and has flown to space with a crew 6 times. That figure is, of course, subject to change in the near future, and that's also the case for New Shepard. So, through all of history, there's been a total of just 27 crewed suborbital flights. Like I said, the vast majority of crewed spaceflight is orbital. This number's way too low for any kind of meaningful statistical analysis. However, let's add all the major incidents to our diagram, or all the known ones anyway. Working chronologically again, we're going to, and I want you to listen extremely carefully to my wording here before you jump in the comments. We're going to include major safety incidents for flights that either reached space or were intended to reach space. Okay, Mercury Redstone. I intentionally missed out a flight, if you can call it that. The first time the system flew on an uncrewed test flight, it made it a total of 4 inches off the launch pad before terminating. Miraculously, it didn't explode, and what followed was one of the most comical engineering incidents of all time. I don't have time to discuss it here, but we'll add it as an uncrewed near miss. The second and final crewed flight was also problematic, with Gus Grissom very nearly drowning on splashdown, so we'll call that a crewed major incident. The X-15. Its final space flight was unfortunately also the final flight for pilot Michael J. Adams. The craft broke up on re-entering the Earth's lower atmosphere. As an aside, I'd be pretty surprised if the other 12 suborbital flights went off without anything major happening. I just can't find anything publicly disclosed. SpaceShipOne is an interesting case. Its second flight was widely reported as a success, thanks to it being the first of 2 flights that would bag it the Ansari X Prize. However, it's less widely remembered that the craft entered an uncontrolled roll during the ascent. There is a clip in the intro to this video, and it's pretty alarming. The exact reasons have never been fully publicly disclosed, but it seems to be a combination of loss of cockpit instrumentation and the craft itself having low inherent roll stability. These factors, in conjunction with the interesting control systems, which we'll get to later, led to the craft rolling 29 times uncontrolled on its ascent. During the incident, a NASA observer on the ground was heard to say, "That is a dead man." However, the pilot was able to recover, and this major incident is largely forgotten in the public eye. New Shepard has never had a publicly disclosed major incident during crewed flight. However, its last uncrewed flight at the time of recording failed, but the capsule was successfully recovered thanks to a crew escape system. I'm not sure how to include that on our diagram. Let's call it a survivable major uncrewed incident. And finally, we get to SpaceShipTwo. None of its 6 flights to space have seen major publicly disclosed incidents. However, a 2019 test flight to space was later found to encounter issues that in any other aviation circle would be considered major safety critical. A seal on a horizontal stabilizer was incorrectly installed, leading to it debonding during the ascent. The loss of the stabilizer during ascent would almost certainly have led to a loss of control. Todd Erickson, former VP for Safety and test pilot for Virgin Galactic, went on to say, quote, "I don't know how we didn't lose the vehicle and kill 3 people." End quote. The 2021 flight with Branson aboard did result in a temporary loss of their FAA certification due to straying outside their pre-assigned flight path. However, there is no reason to be sure this compromised crew safety, so I'm going to be charitable and leave it out. Comparing SpaceShipTwo to prior launch systems is tricky. If we exclude SpaceShipOne, since it was descended from it, it's tempting to compare to the X-15 since it's a spaceplane, but the two were built in entirely different eras and for entirely different purposes. Its contemporary, New Shepard, is a separate design altogether. However, of 21 crewed flights in history, 1 resulted in a fatality and 3 resulted in near misses. That is about a 15% probability of the crew being in significant danger based on historical data. It's also worth noting there have been major incidents in all 3 of my categories of spacecraft. I'm not sure many observers would consider this as acceptably safe. If SpaceShipTwo is indeed acceptably safe, it must incorporate truly revolutionary safety measures to bring this percentage down significantly. Going forward, let's try to ascertain whether this is indeed the case. In any other recent historical setting, SpaceShipTwo would be classified as an experimental vehicle, and one with very few test flights at that. We're going to get into why it's not required to legally operate as such later. For now, let's look in detail at its test flight history. Then we'll move on to its design and safety systems. I've skirted around the elephant in the room for long enough now. SpaceShipTwo had a fatal incident in 2014. I'm not going to dwell on it since the details are well covered elsewhere. In short, the pneumatic feather system was activated too early in the flight, leading to a premature deployment and breaking up of the craft. Amazingly, the pilot, Peter Siebold, was thrown clear of the wreckage and was able to parachute to Earth, albeit with major injuries. The co-pilot, Mike Aylesbury, did not make it. We'll come back to this incident again, but I want to be clear that although every flight to space has brought the crew back alive, not every flight of SpaceShipTwo has done the same. A prior test flight in 2011 also led to a serious incident, very nearly resulting in the loss of craft, crew, and probably Virgin Galactic as a whole. The intention was to release SpaceShipTwo from its carrier aircraft and perform a glide test. For reasons that are not entirely clear, SpaceShipTwo rapidly entered a spin. I personally did spin recovery training in a light aircraft 12 years ago, and I still remember the procedure despite not flying for more than a decade. It's something absolutely drilled into you. In this case, pilot Mark Stuckey followed the recovery procedures to no avail. He then tried some ad hoc remediation learned from his extensive experience, still to no avail. As a last ditch, with the craft falling out of the sky, he deployed the feather system. Now, the feather system is a variable configuration tail boom system, and we'll discuss it further later. It was not in the written procedures, and not something that had been practiced before, but it worked, allowing the craft to be brought to a precarious landing. Stuckey's astonishingly unconventional thinking saved the lives of 3 people. The incident was kept under wraps, and only became widely known publicly a few years ago. Another major incident occurred in 2013 during a rocket fire flight test. The rocket was fired for 16 seconds, and the craft flew on a limited ballistic trajectory in the stratosphere. To simulate a space flight, the feather was deployed in the thicker air of the stratosphere. This caused it to begin raising above its rated in-atmosphere speed, something of a precursor to the 2014 breakup. Little else is known about this incident because, unsurprisingly, Virgin Galactic haven't publicly disclosed anything. And we've already discussed the near loss of a horizontal stabilizer in 2019. In a rare case of self-reflection, Virgin Galactic hired a retired Boeing executive to conduct a safety review following this incident. However, the resulting 40-page report has never been made public or even shared with Virgin Galactic's flight test director. So, as will be the case throughout this video, we do not know whether sufficient remedial action was taken following this incident. In fact, we wouldn't even know about the incident had it not been publicly revealed by a combination of embedded journalists and former Virgin Galactic employees speaking out. Virgin Galactic have done everything in their power to keep it quiet, so as to avoid spooking future customers. I suspect a major contributor to the somewhat sketchy test history of SpaceShipTwo lies with its predecessor, SpaceShipOne, and the motives for its design. SpaceShipOne was constructed to win the Ansari X prize, a $10 million prize for the first privately funded craft to take a crew to space twice within 2 weeks. I remember this well. I was 15 years old at the time. NASA had effectively hobbled themselves with the expensive death trap that was the shuttle. There was much media hype at the time, and it was collectively decided that the moment was pivotal enough to warrant the retirement of SpaceShipOne, allowing for its permanent preservation in the National Air and Space Museum in Washington, D.C., which is a fantastic museum, by the way. If you have a chance to go, do. Burt Rutan stated that no governments are required for spaceflight, and arrogantly declared NASA, or naysay, as he rather cringily kept calling them, were quaking in their boots. What actually followed was a 17-year hiatus until the next crewed private suborbital flight. Much as was the case with government agencies, it soon became apparent that orbit is where the real prize is, and led by SpaceX, the vast majority of private investment was directed at orbital spaceflight. It's difficult to ignore the fact that the X Prize may have actually set back spaceflight. Had SpaceShipOne's fledgling spaceflights not been so publicised and sensationalised, the craft would have almost certainly been flown many more times to better understand its aerodynamic and control characteristics. I imagine it would have been iterated upon, and scaled composites would have gained a comprehensive understanding of supersonic and suborbital flight systems. A hypothetical example of what I consider to actually be innovation. Instead, they were almost immediately contracted by their new partner, Virgin Galactic, to design a passenger-carrying model. And this led to the initially hasty development of SpaceShipTwo, essentially a scaled-up version of SpaceShipOne. In an ideal world, we'd have seen dozens of space flights from SpaceShipTwo before taking paying customers up. Again, that would broaden Virgin Galactic's and the wider world's knowledge of spaceplane mechanics. But unfortunately, the need to make a relatively rapid return on investment appears to have precluded what I would call true innovation. And let's be crystal clear here. I am not saying private investment always hinders innovation. Look to SpaceX's Falcon, Rocket Lab's Electron, Arianespace's launchers, Orbital Science Corporation's Pegasus, and others. And that includes Blue Origin's upcoming orbital offerings. These companies either chose to or were bound by appropriate regulations, which forced them to embark on a comprehensive test and certification program before launching highly innovative systems commercially. So, I think it's time we discuss why Virgin Galactic have faced no such obligations. SpaceShipTwo is licensed for commercial space transportation by the Federal Aviation Authority, or the FAA. Virgin Galactic were happy to make a great fanfare about that when they obtained it in 2018, and subsequently re-obtained it in 2022. However, I'd argue that that statement is extremely misleading. In the US, if you pay to take a flight in an aircraft, that aircraft must be certified by the FAA. The airworthiness certificate is a third-party verification that the aircraft is considered safe by FAA standards. FAA inspectors oversee design, production, and continued airworthiness certification for all registered commercial aircraft in the US. As I've discussed in previous videos, this is expensive but essential. I'm not an aeronautical engineer, but when I get on a Delta Airlines flight, for example, I know that aeronautical engineers have performed relevant safety checks on the design and maintenance of that aircraft, so I can be confident that it's safe to fly. SpaceShipTwo does not have an airworthiness certificate, and neither does New Shepard for that matter. Nor do they have any other third-party certification or disclosed adherence to standards by relevant bodies such as NASA. So what is the nature of this FAA license then? It exists solely to, quote, protect the public health and safety, safety of property, and national security and foreign policy interests of the United States, end quote. In other words, the FAA only attempt to minimize the risk of individuals and property on the ground being hit by a falling spacecraft. They provide no checks or assurances regarding the safety of passengers in the craft itself. SpaceShipTwo is not certified as safe for travel by any third party. I believe, along with New Shepard, this is unique in commercial flight in the US. I think it's a fair assumption that, in general, a spacecraft is inherently more risky to travel in than a standard passenger aircraft. So how on earth did this situation come about, where an inherently riskier mode of transport requires no safety certification to carry passengers? The superficial answer is removing regulations to promote innovation. The more directly worded answer is political lobbying. Following the success of SpaceShipOne, Burt Rutan publicly stated he would go on to certify future craft with the FAA for passenger flight. Now, I'm not here to critique Rutan's engineering prowess much. The man is one of the greatest aircraft designers of all time. But his public opinions of regulation are, let's say, a bit libertarian. He clearly stated on multiple occasions that his desire to certify passenger carrying systems was to prevent legal action in the case of an incident. But this didn't last long anyway. Later in 2014, enthralled by the prospect of a burgeoning private space tourism industry, followed by heavy backing from the industry itself, Congress passed the Commercial Space Bill. Included in this bill was an 8-year moratorium on FAA regulations for passenger safety on human spaceflight systems. That moratorium has since been extended to October 2023, and I'll be surprised if it's not extended again a couple of months after I release this video. The intention of the moratorium is to allow the fledgling industry to develop without restriction or regulation. Comparisons were made with the early aviation industry, which was also unregulated. I don't have time to go into full details now, but these comparisons are superficial at best. Passenger aviation accidents in the 1920s were so common that the industry voluntarily persuaded Congress to require FAA regulation to improve safety as a whole. I'll leave more details in the sources. Removal of regulation for testing is one thing. Removing it while allowing operators to carry fare-paying passengers is another. So, how are passengers to assess whether SpaceShipTwo or any other spacefaring system is acceptably safe? This is where we finally get to the video title, Informed Consent. Let's go to Virgin Galactic's annual report and let them explain informed consent in their own words. Quote, under US federal law and the Commercial Space Launch Act, that's CSLA, operators of spaceflights are required to obtain informed consent from both participants and members of the crew for any commercial human spaceflight. End quote. They go on to detail how the relevant federal laws also protect them from financial liability in case of an incident. Though that is a common topic of discussion, I do not care about operators being sued or not. The focus of this video is on safety of the system itself, and how effectively that level of safety, or lack thereof, is communicated to customers. And while we're here, I do wish Virgin Galactic would stop referring to their prospective customers as astronauts. It's... Anyway, in plain English, all customers of Virgin Galactic must sign a waiver, declaring that they consent to flying on what, as we have already discussed, is essentially an experimental spacecraft. That is informed consent. I argue that we can quite reliably drop the word informed. I think I've already made pretty clear that there is no amount of money you could pay me to fly in SpaceShipTwo, and that is because I have no idea how safe it is. Due to the lack of flight history, no one knows how safe it is. However, knowing the following would go some way to informing my choice. Full details of every test flight, with flight envelope findings, conclusions, and subsequent actions. Full details of rocket motor tests. Has the motor ever catastrophically failed on a test stand? How is its integrity ensured prior to and during a firing? Full maintenance and inspection records for all flight-critical systems and materials. Full records of pilot training, including hours flown in simulator, the craft itself, and the White Knight 2 mock-up. If I had this information, and no doubt much more, I'd still be nowhere near knowledgeable enough to make a judgment based off it. If I could afford to, and actually wanted to, fly on SpaceShipTwo, I would hire a relevant team of engineers and technicians with expertise in the above to collate this information and provide a safety assessment. The astute amongst you will know I have just described an audit process, really just a step to certification. Anyway, even if I wanted to do this, I could not. Some of this information is not publicly available, as it constitutes a commercial secret for Virgin Galactic, and they do not wish to make it public. In fact, Virgin Galactic do not have a single published patent, which was another obstacle to researching this video. The rest can't be published due to international arms trafficking regulations. So, we have an uncertified spaceflight system with a total of 6 prior spaceflights with 1 fatal test incident, at least 1 near-fatal test incident, and at least 1 safety-critical flight incident. And through corporate secrecy and arms trafficking regulations, we cannot access any meaningful technical information or test data to make an engineering-based risk assessment. I think it is quite clear that no customer can be informed when giving consent to fly on SpaceShipTwo. I'd now like to take a closer look at SpaceShipTwo itself. I can only carry out a limited engineering risk assessment due to the lack of available information previously discussed. However, there's still plenty we can cover. And in the interests of balance, I'd like to discuss some of the systems that I believe make Virgin Galactic SpaceShipTwo safer to fly in than it would otherwise be. First of all, the motor. SpaceShipTwo uses a class of rocket motor that's rarely used for crewed spaceflight. Let's quickly discuss the three families of rocket engine. All rocket engines require fuel to be burnt and exhaust ejected through a nozzle at high speed. To ensure a vigorous and complete burn, the fuel must be mixed with oxidizer in the combustion chamber. Achieving this safely and reliably is something we're still a long way from. Solid rocket motors are something we're all familiar with. If you've ever launched a firework, you've launched a solid rocket motor. Here, the fuel and oxidizer are both solid and combined together in a single contiguous mass. If that sounds alarmingly similar to heavy ordnance, that's because it is. Solid rockets are seldom used in isolation for crewed flight, as once they're lit, they cannot be put out. Just to give some context to that statement, Mike Mullane in his book Riding Rockets made very clear that once the shuttle's solid rocket boosters were lit, that thing was leaving the launch pad regardless of whether the hold-down bolts released. And even if the bolts had the strength to hold the shuttle in place, the exhaust from the boosters was not hot enough to melt the steel hold-down structure. It was hot enough to boil it. At the other end of the complexity controllability spectrum are liquid-fueled engines. Every crewed spaceflight, with the exception of SpaceShipOne and SpaceShipTwo, has used liquid-fueled engines as the primary means of getting to space. They're throttleable and can be shut down at any point during a flight. However, this comes with the drawback of complexity. Liquid fuel requires complex plumbing and turbopump assemblies, and the fuel itself is far from benign. A fuel leak carries high probability of fire, and if the fuel and oxidizer somehow make unwanted contact, an explosion, as we've seen many times in the past. Had SpaceShipTwo used a liquid-fueled engine, Peter Siebold would not be with us now. Hybrid motors, on paper, offer improved safety over both types. With less complexity than liquid engines, they combine a solid fuel with a liquid oxidizer. In fact, I have one right here. I built this a couple of years ago, but I've never got round to firing it. This video is already long enough without my personal project, so we'll test fire it in another video. But let's quickly see how it works. My motor uses 3D printed fuel. It's just PLA plastic. It's benign, so poses no significant flammability risk. For the oxidizer, it uses nitrous oxide in this little cylinder. And yes, that's why one of those appeared in the previous video. Using a remote igniter, I can create a flame here, and then drop a weight here to puncture the cylinder. The nitrous oxide breaks down to nitrogen and oxygen in the flame, thus creating an oxygen-rich environment here. The fuel burns vigorously in this environment, creating a high-velocity exhaust through the nozzle. SpaceShipTwo's motor is the largest hybrid ever used for crewed flight. It's honestly not too far in design from my little rocket motor. It too uses nitrous oxide to burn a solid fuel. In this case the fuel is still plastic, but it's HTPB rather than PLA. I think Virgin Galactic should be on the whole commended for using a hybrid design due to its inherent safety over other systems. Scaling up the motor from that used in SpaceShipOne has proved significantly more difficult than expected, however, but sticking with a hybrid design does mitigate fears of volatile fuel handling and lack of throttleability. We should note that the choice to use a hybrid motor is almost certainly the reason SpaceShipTwo requires a carrier aircraft. Nitrous oxide and solid fuel motors just don't have the specific impulse achievable by liquid engines. Or in more colloquial terms, no one's yet been able to design a hybrid motor that can burn long and strong enough to get a crew all the way to space. However, with a carrier craft, SpaceShipTwo can begin its rocket booster descent from 18% of the way to space with about a quarter of the required speed. In addition, it's released above about 90% of the Earth's atmosphere, so has to contend with much less atmospheric drag. As we see here, reaching space without the carrier vehicle would require significantly more fuel and oxidizer, leading to a craft more akin to New Shepard. I do, however, have a few safety concerns with SpaceShipTwo's motor. As is the case with every aspect here, I cannot quantify the extent of the risk. These are just additional unknown factors that prospective customers face when trying to give informed consent. First of all, the motor does actually use some liquid fuel. The NTSB report from the 2014 crash shows 2 fuel tanks in addition to a helium header tank. No details are provided, but the fuel tanks likely contain methane, I believe, which could be fed in during ignition to reduce the chance of a hard start. Hybrids are susceptible to hard starts, which can cause catastrophic failure, and a flow of liquid fuel on ignition can help mitigate this risk. However, the additional plumbing and presence of a volatile fuel source may also partially diminish some of the safety advantages of a hybrid motor. Additionally, prior to the development of Rocket Motor 2, nitrous oxide was almost universally viewed as a stable and relatively safe substance. This changed in 2007 when a tank of nitrous oxide exploded during a cold test at Scaled Composites, resulting in 3 fatalities. The likely cause was a thermal decomposition reaction caused by a malfunctioning electrical pump in the nitrous line. Normally, this reaction will be self-quenching, but due to a number of factors that are still not fully understood, the reaction propagated back into the main tank, causing an explosion. Although the final OSHA report on the incident placed blame on Scaled Composites, I'm actually inclined to grant them some leniency. The mechanism which created the explosion was sparsely understood at the time. Nitrous oxide is present in almost every dentist office and operating theatre worldwide. Though, please do note, third-party experts were much more scathing than me in their assessment, placing the blame squarely with Scaled Composites. Nevertheless, SpaceShipTwo carries 4.5 tons of nitrous per flight in a tank of unknown composition. It is unknown due to the previously mentioned arms trafficking restrictions. So once again, another risk of unknown magnitude. The second system for which I believe Scaled Composites and subsequently Virgin Galactic deserve praise is the feather system. Let's go back to that X-15 crash we mentioned near the start of the video. For suborbital flight, the X-15 would climb above the vast majority of Earth's atmosphere and then re-enter on a ballistic trajectory. When I say ballistic trajectory, what I really mean is it had come screaming back into the thicker stratospheric air at Mach 5. With only a primitive fly-by-wire system available back in the 1960s, this meant the pilot had to hold a specific nose-up attitude manually, while the craft bled off this extra energy. And I don't think it requires a degree in aeronautical engineering to guess that the X-15 was not a particularly stable aircraft. Just look at it. The 1967 incident and breakup of the craft was caused by the pilot slightly deviating from the required attitude, possibly due to an electrical failure, leading to an unrecoverable spin. In fact, the pilot during that incident, Michael J. Adams, was actually a personal friend of Burt Rutan. And Burt acknowledges that the crash was the inspiration for Spaceship One's most innovative feature, the feather. The vessel's tail boom sat on a hinge, which could be raised prior to re-entry. As long as the feather was deployed, the craft was passively stable, always falling back to Earth in a safe orientation. SpaceShipTwo uses exactly the same design principle, hinged tail booms, which guarantee a stable descent from the upper atmosphere. Considering the feather design in isolation, and not the ancillary systems which interface with it, I believe Virgin Galactic should be commended for following a design philosophy which effectively removes one of the major threats to the crew during a trip to space. Though this is not a billionaire showdown, and we're focusing on safety here, a very quick digression is appropriate while we're discussing positive aspects. Safety and ethical considerations are intimately linked, and I think it's important to give credit where it's due. Virgin Galactic were pursuing funding to the tune of $1 billion from the Saudi Arabian royal family in 2017. However, Branson refused the offer following the assassination of Jamal Khashoggi in 2018. In a world where we're often led to believe morals keep you poor, I have nothing but admiration for this. Elon Musk did not do the same when searching for co-investors to fund his purchase of Twitter a few years afterwards. There are two highly visible design choices present in SpaceShipTwo that give me great concern. The first is quite broad and has played a part in 3 of the major flight testing incidents I've discussed prior. It's the control system and its lack of automation. Rattan has historically chosen to avoid working with systems he does not understand, with the apparent exception of nitrous oxide. He revolutionised the use of composite materials in aircraft design, but most of his designs rely on surprisingly antiquated control systems. Julian Guthrie provides a lot more insight into Rattan's propensity to cut back on systems he considered non-essential in his excellent book, How to Build a Spaceship. I won't go into details here, but this leave out the non-essentials, just make sure you have really good pilots approach is not one seen anywhere else in commercial aviation. I extensively discussed how non-essentials can quickly become essentials in my previous 2 videos. Let's discuss reversible controls. If you grab a control surface on a light aircraft and move it, the joystick will move in unison. That's because the 2 are physically linked by a cable. There have been a total of 3 supersonic aircraft in history with reversible controls. The first was the Bell X-1, the first supersonic aircraft ever built, which flew in 1947. The other 2 were SpaceShipOne and SpaceShipTwo. I spent a couple of days verifying this, and it absolutely appears to be true. The Bell X-2, the X-15, the F-100, MiG-19 all had a hydraulic system between the stick and the control surfaces. Equally surprisingly, White Knight 2 also has reversible controls. In fact, I'm not even able to find info on whether it has electrical actuators. I think the entire aircraft might be flown entirely by stick and rudder. I want to drive the point home how unusual this is. To do that, let's look at a great paper from the US Air Force Flight Dynamics Laboratory from 1968. Why am I choosing such an old presentation? Because fly-by-wire in supersonic aircraft was already the norm back then. And also, older papers tend to be a bit easier to understand and communicate. So, we start with Snoopy flying a World War I era biplane and asserting that security is a mechanical flight control system. I think now, in 2023, that is still a common misconception. For the uninitiated, a physical link between the pilot and the control surfaces feels reassuring. However, if we step back into the real world, it's readily apparent that this is a fallacy. And the author does a great job pointing this out. This paper focuses on electrical actuators to assist the pilot. However, since it was written, almost every large and/or supersonic aircraft also has a hydraulic system between the pilot and the control surfaces. This acts as a force multiplier and allows the pilot to actuate the surfaces with much reduced physical effort. Anyway, in contradiction to established design, SpaceShipTwo does not have a hydraulic system. Focusing on electrical actuation only, the author goes on to detail the various redundancies and measures that must be taken to ensure control can be maintained in the case of fly-by-wire system failures. He discusses quadruple redundancy, 2 fail-still-operate systems, entirely independent power and sensor systems, and how failovers can be automatically and manually initiated by the pilot. Our paper ends with Charlie Brown asserting that security is a fly-by-wire control system, and the subsequent 45 years have proved him correct. Since this paper was written, 2 civilian supersonic airliners flew extensively, the Concorde and the Tupolev Tu-144, but the less said about that one, the better. Neither had a crash due to a fly-by-wire failure. Similarly, every supersonic jet built since had hydraulically actuated controls and some kind of fly-by-wire. Whoa, okay, correction from Alex a few hours before the video's published. I don't know why I kept mentioning hydraulics here. Yeah, lots of large airliners require hydraulic actuators to move the control surfaces, but plenty of aircraft, particularly smaller ones, use electric actuators. That is one of the purposes of electronic fly-by-wire, to get rid of all those hydraulic lines. SpaceShipTwo has electrical actuators for supersonic trim. In fact, there's speculation they may have been repurposed somewhat recently and used with a computer to perform some kind of stability augmentation. But the controls are still directly connected. So those tabs, those electronically actuated tabs, are not part of a full fly-by-wire. They only have limited control authority. And this augmentation system, if it exists, is most certainly not externally certified, and it's been to space a maximum of 5 times at the time of recording. Okay, back to 2 weeks ago, Alex. There have been incidents due to modern control systems being implemented incorrectly, but reversible controls in anything other than light aircraft are something that largely belong in the distant past. The aforementioned X-15 crash was caused by a partial failure of the fly-by-wire system. However, subsequent study of the failure points makes it clear that the system was improperly implemented by modern standards. The X-15's fly-by-wire used unqualified components, suffered from a lack of risk assessment, and poor human factors considerations. Fly-by-wire systems were in their infancy back in 1967. We have nearly 50 years of learnings to draw on, and current systems avoid these shortcomings. Most light aircraft are inherently stable for most flight scenarios. When I say inherently stable, I mean if you let go of the controls, the aircraft will either stay in its current orientation, or in some scenarios actually return to level flight. So, in these cases, reversible controls are fine. For supersonic aircraft, however, things become weird. Once we start to get near and beyond the sound barrier, airflow backs up ahead of the aircraft and can change the behaviour of the control surfaces. Control inputs that would normally move the aircraft in a linear manner often result in unpredictable, non-linear behaviour due to the change in pressure and flow regime at supersonic speed. Look at SpaceShipOne. It had a high wing format with a dihedral, excellent for roll stability at subsonic speed, but when flying supersonic, highly unstable in the roll axis. To build an aircraft that is reasonably stable in both subsonic and supersonic flight, we usually need to physically change the configuration of the aircraft itself when going supersonic, or use a flight computer to artificially maintain stability by augmenting human inputs at a faster speed than a human is physically capable of doing. SpaceShipTwo achieves the former, and it does so via electric actuators, which adjust the position of trim tabs on the control surfaces. The shape of the surfaces is changed by the pilot entering trim inputs once the vehicle has gone supersonic. So although the controls are reversible, there is at least some kind of secondary system to adjust the flight characteristics when flying supersonic. The Bell X-1 had a similar system, raising the horizontal stabilizers to bring them out of the high-pressure airflow at supersonic speed. I can't, however, find any information on whether this electric system assists the pilot in maintaining stability via a flight computer. As it is stated there is no fly-by-wire on SpaceShipTwo, my assumption is that it does not. If the pilot accounts in Nicholas Schmindl's book Test Gods are to be believed, there is no reason to believe they're fabricated, but I haven't used this book as a single source as it may be biased. Supersonic flights of SpaceShipTwo are mentally taxing, with pilots constantly fighting to hold a given orientation, particularly against unwanted roll. This requires significant physical strength due to the absence of hydraulic control actuation. With no flight computer and fly-by-wire, the entire workload is placed on the pilot to hold the aircraft in a stable position. And if the aircraft ends up losing stability, which can happen extremely quickly and in an unpredictable manner when flying supersonic, it is entirely up to the pilot to restore it. No computer assistance available. I cannot stress enough This is unique in currently operational supersonic aircraft. This highly unusual rudimentary control system, and the wider lack of automation as a whole, has been the direct cause in at least 3 incidents and regulation breaches experienced by SpaceShipTwo so far. Remember how the 2014 breakup was due to the feather system being deployed early? The co-pilot had a window of several seconds during the transition to supersonic flight to flip a switch to unlock the system. This would ensure it's functional and would fully deploy for re-entry. If no unlock confirmation was received, the motor would be shut down and the craft glide back to the runway. On the surface, this is a good safety measure, a function check to ensure the craft will survive re-entry. In reality, what would be a relatively simple task for a computer, or to be honest, an extremely simple task for a computer, increased task loading on a pilot during one of the most stressful phases, if not the most stressful phase of the flight. In 2014, that switch was thrown early, deploying the feather at high speed in a relatively thick atmosphere, destroying the vehicle. Though Virgin Galactic eventually brushed this off as pilot error, which is technically true, for decades, engineers in all sectors have done everything possible to design the operator out of crewed systems. We know operator error is extremely common, so we try to reduce the chances of it happening in the first place through appropriate design. This is known as human factors design. Put another way, would you be happy as a passenger in a plane that contained a one-touch, please make the plane explode button in the cockpit during a portion of the flight? Though Virgin Galactic state they've designed out that particular procedure, SpaceShipTwo is very much still a manually flown, low automation spacecraft, and therefore subject to the relatively common curse of human error. In fact, Virgin Galactic are proud to show that off in their sales brochure. We know Spaceship One wasn't particularly stable in flight. Spaceship Two has had past stability issues, and let's be honest, it doesn't look stable, but Rattan is one of the best airframe designers in history, so I'm not going to go there. Regardless of its inherent stability, we do have to question whether the 2011 control loss incident would have even been possible given the presence of a proper flight computer and fly-by-wire system, as we see in every other operational supersonic vehicle in operation today. Were the minor aerodynamic changes made to the craft since 2011 sufficient to prevent a repeat incident happening? Could that incident happen at a lower altitude where the feather wouldn't be able to save the crew? I don't know. I'm assuming you don't either. The other highly visible design choice that unsettles me is a natural consequence of choosing a spaceplane design. In fact, this consideration may preclude spaceplanes from being truly considered as safe well into the future. It's the lack of a launch escape system, or LES. Spaceship One and SpaceShipTwo are the only suborbital spacecraft ever built that are unable to eject or boost the crew compartment free in the case of structural failure. Broadly speaking, there are 2 phases during any spaceflight where a catastrophic failure is relatively likely: the boost phase and the re-entry phase. We've already discussed how Virgin Galactic have essentially designed in inherent safety during re-entry. Due to the unpredictable nature and necessary low safety margins required for rocket design, catastrophic failures of both the engine and vehicle structure are relatively common during the boost phase for spacefaring vehicles historically. As a result, most space launch systems are equipped with a crew escape system. The only 3 systems that have not been thusly equipped, that's orbital and suborbital, are the shuttle. A LES would likely have saved the lives of the Challenger crew. Spaceship One and SpaceShipTwo. We've discussed the 2014 breakup incident already, but again, a LES would likely have brought both pilots home. The surviving pilot did have an automatically deploying parachute, a kind of rudimentary LES, I suppose, and that is one factor in the unlikely chain of events that allowed him to survive. no crew fatalities have ever occurred on the upward leg of a flight to space in a LES-equipped system. In fact, they've saved the lives of crews on 2 occasions, both on Soyuz launches in 1983 and again in 2018. In addition, the most recent uncrewed launch of New Shepard suffered an engine failure, triggering the LES and returning the capsule with its scientific payload to Earth safely. Unlike the pilots of most high-altitude aircraft, neither the pilots nor the passengers in SpaceShipTwo wear pressure suits, so a loss of cabin pressure would expose all occupants to the vacuum of space. But in the only commercial launch to date, crew are shown donning parachutes. But this is a far cry from the full-blown escape systems we see elsewhere, or even from the ejector seat of the X-15, which sounds like an absolute nightmare to design, yet was still deemed necessary to improve crew safety for the craft. Of course, a LES is far from a silver bullet, but given the historical failure rate of space launches and the proven record of well-implemented escape systems, I find it absolutely astonishing that any sufficiently informed participant would be happy to take a flight in a vehicle where a significant portion of the flight guarantees their death in the event of a historically common failure. And I keep reiterating, but what is the chance of a catastrophic structural failure on SpaceShipTwo? Say it with me, we don't know. I'd like to conclude by challenging a more qualitative argument for the safety of Virgin Galactic as a whole. Branson flew in it, so it's likely to be safe. Or sometimes, the pilots wouldn't fly it if it was unsafe. I don't actually need to tackle this argument head on, because it's one I have direct experience with. Back in 2012, when I regularly flew as a helicopter passenger to offshore oil platforms in the North Sea, there were a couple of major incidents that very much directly affected me. Within the space of 5 months, 2 Eurocopter EC-225 helicopters were forced to ditch in the North Sea. In both cases, all crew and passengers survived, and the issue was found to be due to fatigue cracking in the main gearbox. Much like an explosive rocket motor failure basically guarantees the loss of a spacecraft, a gearbox failure guarantees the loss of a helicopter. Engine failures can be dealt with. Helicopters can be auto-rotated to a landing. Gearbox failures mean the rotors stop turning and you fall out of the sky. In both ditching incidents, the pilots responded to a warning light before the gearbox actually failed, and were able to ditch safely in time. All EC-225s were grounded for a couple of years while the root cause was investigated. Various remedial actions were taken, but it was not deemed necessary to make major material or structural changes to the gearboxes themselves, although the main shaft was redesigned. The type was returned to service in 2014. In retrospect, somewhat amazingly, the main argument I was given by my superiors was, if it wasn't safe, the pilots wouldn't fly it. Looking back, this is just a more refined version of, well, he dares do it, why don't you? Followed by flapping arms and making chicken noises. And I don't want to take credit here. At the time, I was far less versed in risk management. I was happy to accept that argument back then. I think we can all see where this is going. It took just a couple of years. In 2016, an EC-225, which had been returned to service and was flying in the Norwegian sector, had a main rotor detachment shortly after takeoff. There were no survivors. The cause of failure? Fatigue cracking in the main gearbox. Shortly after this video is published, 4 passengers are scheduled to roll the dice with Virgin Galactic. One of them currently studies at Aberdeen University, barely a stone's throw from where I live. I wish her and her fellow passengers the best of luck, though I have no idea how much of it they need. Thank you very much for watching.